I don't know why, but I love me some conservation of energy problems. Call me weird, call me what you will. They're great. Alright, so we got this cylinder. Is that what they call it? Yeah, uniform cylinder. And here's the center. And this is the radius. But we're rotating about an axis through the cylinder that is not at the center. And it just shoots right through. Like that. Right? So it's going to kind of wobble, you can imagine. It's like, kind of like, what do you call it? Roasting a turkey or chicken or something in those spinny stoves. I have no idea what those are called. Anyway, so we need to find overall the angular speed as it reaches its lowest position. So I guess it starts with the longitudinal axis the same height as the axis. So it basically starts. Let's look at a front view now. So here's the front of the cylinder, and here's the center. So this pivot point is at the same height as the central axis. So it starts off like that. Then it's going to drop down like that so that the center is below, so it's going to actually fall along this path, the center point. Right, so if you were to draw this later on, maybe it's going to be a little bit lower. That's where conservation of energy comes in, because it loses height, gains kinetic energy. So it's going to be like, this is at the same height, because that's the pivot point, so it's going to be here. That hasn't changed height. Of course, I didn't draw it perfectly. And then the center now is below. Alright, so first off, we need to find the I of this, the moment of inertia of this cylinder, in order to use that in the kinetic energy, which is used in conservation of energy. So this is the I com of a cylinder plus mh squared, because it's not rotating around the center of mass, so we need the parallel axis theorem. A cylinder happens to be 1/2 mr squared, that's not too bad, plus mh squared. 1/2, the mass is 20, and the radius, this length, is 0.1 squared, plus, and the mass again is 20, and the distance from the center to the pivot point, this little distance here, is 0.05. And you just calculate that, and you get 0.15 kilogram meter squared for the I. We'll just call it I, because in part B we got gravitational potential energy is going to turn into rotational kinetic energy, so that's just mg. Now, I guess I could use h, because it's the same thing, isn't it? It is. So I'm just going to use h. That's just a coincidence, by the way. Typically, well, you don't need me to tell you that. Just so happens that this h is the actual height that it drops. And so we'll leave that there. And this is 1/2 I, which is what we just found, times omega squared, which is what we're looking for. And so the mass is 20, 9.8, and h, that little h is this same deal here, 0.05. That equals 1/2 times 0.15, which we found up here, times omega squared. Solve for omega. You get 11.43 radians per second. That was cool. I like it. Alright, that's all of the sample problems I will do for chapter 10. Hopefully these give you a good idea of how to solve the book problems and the quizzes and tests coming up. So, yeah. Alright, now on to chapter 11.